Okay. Hi, my name is Callie Wilson, and this is my Physics 2212 Lab 6 Magnetic Molasses. Introduction. In this lab, a bar magnet will be released to fall down an aluminum tube that is constructed. The purpose of this lab is to study the data from the model of the bar magnet falling through the tube and compare those results with the computational model that is created and run. The lab will showcase the Biot-Savart law, Faraday's law, and as well as Newton's laws of motion. The system is bar magnet, the surroundings is everything else. The experimental model is aluminum tube and bar magnet, and the computational model is GlowScript. As for results preview, the experimental time I got was like 1.034 seconds, and the computational time was like 3.856 seconds. So the Biot-Savart law, the equation that describes the magnetic field that is generated by a constant electric current. Faraday's law, an electromotive force is produced when changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux. Newton's second law, net force is equal to the change in system's momentum over change in time. And then Newton's third law, each action force has an equal and opposite reaction force. For this experiment, one person in the group held the tube, as you can see, and a magnet, and then dropped the magnet so it would fall through the tube out the other end. Another partner would time each experiment and record change in time between the magnet entered the tube versus when it exited the tube. The induced currents in the tube create an upward magnetic force while the magnet is falling, causing a slow descent through the tube. The results for this experiment, the tube length was like 0.045 meters, tube width was 0.005 meters, inner tube radius 0.02 meters, outer tube radius 0.03 meters, magnetic mass 0.02 kilograms, magnetic permeability, as you can see there, and then average time, as you can see that I calculated, is 1.034 seconds. For the computational model, I edited the geometry of the tube lines to match my specific tube. Then I edited the properties of the magnet, edited the code in step 2 to create a function to calculate the magnetic field of the bar magnet, and then edited step 3 to calculate the magnetic flux of the bar magnet. Continuing this computational model, I changed the F-grav vector to represent gravity, set ring current to be negative charge, and the flux over ring radius. Um, I edited steps 5 and 6 to calculate the B field in each ring at the magnet falls. As the magnet falls, and then I edited the net force to be the force of gravity plus the magnetic force, and updated the bar magnet's velocity and positions. And you can see all this in my code in the pictures to the right of my words. Now, here are the results of my model. Here's the graph and the picture. As you can see down here, time in seconds, 3.856. Some errors and assumptions. Some assumptions was that it was assumed that the bar magnet acts as a magnetic dipole, that the air resistance is negligible factor in the experiment, and only two forces are at play, or gravity and the magnetic force. And then the errors, obviously, human error is always the biggest, especially when it comes to measurement. Friction inside the aluminum tube can also be present. And then air resistance is also an error to think about. And then observation statements, which colors correspond to clockwise and counterclockwise current. Using Lenz's law, blue corresponds to clockwise and red to counterclockwise. What would happen if the magnet flipped? The current directions would flip. How does the real world delta t compare to the computational delta t? The real world time was shorter than the computational time. I assume this is due to error in measurement, honestly. And then what does the plot shape tell you about the forces acting on the magnet? So it tells us the force of gravity is greater than the magnetic force at the entrance and exit of the tube, but the forces are equal within the tube. Now for the discussion, what if resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The magnet would be even slower, as decreasing the resistance would increase the induced current via Ohm's law. And then this would create a stronger magnetic field, and then what holes or slots were cut in the tube, or what if they were cut in the tube? How would this affect the ring's current in your model? So it would make a weaker magnetic field, opposing the force of gravity would be created due to less current rings, so the magnet would fall faster, essentially. That's it. Thank you.